Welcome back. In first module under capacity planning, we discussed about various tools which helps know your database workload better, such as AWR reports, ADDM, active session history reports. We also tried to understand what is database time, and all of these tools are based on DB time model. And now we are going to discuss about approaches for sizing system resource for database deployments. So, as well as we will also talk about how to interpret the stats gathered via these tools. So the first one, database sizing concept, is going to cover about storage as well as IO considerations. So you need to collect detailed storage information for each source database for each of the 4 segment types. That includes tables, indexes, lobs, as well as others. And the AWR matrix, physical read-write total IO requests per second, are used for measuring IO workload of a database instance. So for destination sizing requirements based on ASM redundancy, you need also the IOPS as well as write IOPS separately, since the number of writes required will depend on the ASM redundancy, which is desired at the cloud infrastructure destination. So some of the prerequisites, like you have already gathered the source database, segment type, amount allocated, amount actually used, table space size, redo logs, file size, DB recovery area size. So these all are considered when you are looking at sizing the storage as well as IOs. You need to also estimate the size based on various types and levels of compression you have in your mind when you are considering a new platform. The IO requirements can be collected as IO request per second, that is known as IOPS, IO bandwidth, that is MB per second, and ratio of IO bandwidth to IOPS can be used to characterize each source database workload as either OLTP or decision support system. So reduction in IO requirements achieved by moving to Exadata-based cloud options. So that is another factor we need to think about. Oracle Cloud Infrastructure Database provides advanced compression as well as hybrid columnar compression option that has to be considered or factored during storage and IO planning. So an estimate of how much space can be saved by compressing the data, it again depends on the segment type and database version, and estimates for several types and levels of compressions are available in cloud infrastructure like OLTP compression or hybrid columnar compression. So we'll see in later slides how to use those advisors in order to derive to these kind of information. The another consideration, if you are planning for any Exadata based systems like Exadata Cloud Service, Exadata Cloud at Customer, or autonomous transaction processing databases, dedicated or serverless. So they all are based on Exadata storage server. And Exadata storage server is engineered storage system that provides you certain unique technology of the database machine, and that also involves like a smart scan, a smart flash cache, smart flash logging, IO resource manager, storage indexes, as well as hybrid columnar compression. So the hardware component of Exadata storage server is referred as Exadata cell, and that has to be factored based on how much storage capacity do you need, as well as also you have to keep in mind the performance of the database system. The CPU cores in the Exadata storage servers are dedicated to provide features such as smart scan, SQL processing, and that is done in basically it is uploaded to the Exadata storage. So an estimate of how much space can be saved by compressing the data is important. Depending on the segment type and database version, estimates for several types and levels of compressions are available, such as OLTP and SCC. We estimate how much space we can save if we had to compress a segment, and this package takes a segment and compression type and returns a number which gives us the above information. So number returned is a ratio of the number of blocks when segment is uncompressed to the number of block when the segment is compressed. The package DBMS compression as of now supports tables, indexes, and large objects. So for database version which is less than 11.2, only OLTP compression type on table segments are supported. For target version 11.2 and above, less than 12.102, compression advice will estimate compressed space for OLTP query high, query low, archive high, and archive low can be evaluated. For LOB segment types are high, medium, and low, and any database which is version greater than 12.102, there are some additional compression types like in-memory, no compressed, DML query, low query, high capacity, low capacity, high, etc. are supported. So for index segments, the type of compressions could be high as well as low. So now let's talk about how to size a CPU, and for estimating CPU requirements, average active session plays an important role. So that is compared with the number of CPU available on the system, and if average active session far exceeds the number of CPU, then database performance is likely to suffer. So on the other hand, when the value is significantly less than the number of CPU, so performance would be fine, at least for the database perspective, and if there are any performance bottleneck, they are likely to lie some other places. So average active session is DB time over elapsed time for a particular workload, and reducing database time metric is the main goal for Oracle self-tuning tool ADDM as well as any new consolidation scenario, and it can be measured directly from underlying metric view from active session history samples. So both sample interval and retention period of AWS snapshots are under user's control. So active session history sampling is at 1 second interval, which we discussed in our previous session. So AS is based on database time, and database time is the amount of elapsed time in microseconds spent performing database user level calls. So it includes CPU time, IO time, as well as active wait time, but it excludes any kind of idle wait times. So it does not include the time spent on instance background processes such as pmon, etc. Looking at the memory requirements, we have several processes like SGA and PGA related parameters. Total PGA located which is available in AWR can be used. If PGA aggregate target init parameter value is higher, then we should be considering that. And SGA related advice can be derived from $SGA target advice, or you can get the actual SGA directly from the AWR reports. So you'd be able to see SGA target or SGA max size parameters, which are part of AWR report. So in OCI, a SAPE defines the number of Oracle compute units, that is known as OCPUs. And this is important as the amount of RAM which is available for an instance is tied with the OCPUs in most of the data management options which are available, such as bare metal or database cloud service virtual machines. So when you select a SAPE for your instance, consider the nature of application that you are going to deploy, as well as number of users you expect to use the application, and also how you want to scale the workload in the future. So you need to remember that CPU and memory resource that has to be also used by the operating system. So to determine the SAPE that meets your resource requirement, you may want to experiment with a SAPE and test it with a representative workload. Another important consideration to keep in mind is VM-based SAPes, you can get maximum of roughly 240 GB of memory, whereas in bare metal SAPE, you can get up to 756 GB of DRAM per instance. Dedicated Exadata-based offerings provides 750 GB of DRAM per DB compute nodes, and in a smaller SAPE like quarter rack, you can get roughly 1.5 terabyte of DRAM in a quarter rack configuration. So looking at requirement and sizing consideration, you need to determine the database size and growth rate, and you are going to use basically AWR reports or AWR miner reports or OEM consolidation workbench, AWR warehouse if you have available through Enterprise Manager. You need to determine the IOPS requirement, which you can estimate based on AWR reports or any other operating system monitoring tools. You need to also look at performance requirement, high availability requirement, RTO and RPOs. Network bandwidth requirement has to be also considered for application and database operation. You need to determine the level of control you want to have, such as autonomous, which has serverless and dedicated, versus automated database services like XRCS or DBCS versus any customer managed. So that is going to be a deciding factor, how much control you want to have in the new platform. And finally, like, you are going to validate the sizing using a load testing or unit testing tools such as SQL performance analyzer or database replay, which is provided by real application testing on these platforms. So few more considerations, like if you have an existing Oracle database and you are planning to migrate to OCI, you have several options. So diagnostic pack, which is available on Oracle instances, you would be able to run AWR reports and you can get the matrices like IOPS or Mbps or gigabit per second and so on. Then you need to choose the DBAS offerings such as VM based or bare metal or autonomous or XRCS, depending on the matrices you have collected from these reports. You might consider running these AWR reports during both regular as well as peak workloads, and so you can compare, and based on these reports you can size the data management service, which basically suits your requirement based on either the average workload or the maximum workload. These AWR reports can be generated either using Enterprise Manager or through command line using AWR RPT commands. If your current install has maybe a standard edition, you can probably want to use a stats pack because AWR reports are not available on a standard edition version of database. For rack enabled systems, you should try to pull out cluster wide data, and AWR reports can be fetched for cluster wide for a better analysis. So in addition to database matrices, you should also be able to collect server stats such as physical or virtual, how many chips are there on the server, core per chips or CPU utilization, peak system memory or memory utilization, IO bandwidths, planned CPU growth or any kind of planned memory growth kind of requirements. In order to get AWR report, the command line is under Oracle Home inside RDBMS and admin folder. You have AWR rpt.sql, and if you create them, you will be able to see various parameters or matrices such as read request or write request or database average CPU utilization, SGA size, PGA size, planned IO growth percentage, or any read optimization if you have, considering what kind of storage media is behind the scene, or any write optimization because of flash, or even looking at redo log rates per second, network throughput, network latency rates, database size, byte received via SQL Starnet to the client, IO requirements can be also considered, like IOPS and IO bandwidth MB per second. So these all data will be available within AWR reports, and you can fetch AWR reports for different periods, as I said, like during peak hours or normal hours, or you can also do AWR comparisons. So these all helps you get various matrices which are required for the capacity planning. Another aspect here for sizing consideration is like how to calculate the IOPS. So read IOPS, which is physical read total IO request per second metric from the AWR, and write IOPS are the physical writes total IO request per second metrics from the AWR. So for the source database are required, as well as you need to factor the ASM redundancy which you are going to have at the destination, and this ASM redundancy could be either high, normal, or none, like if you are depending on the external redundancy. Similarly, read bandwidth is physical read total bytes per second metric from AWR, and write bandwidth is physical write total bytes per second from AWR for the source database. So required ASM redundancy is also needed here, which could be either high, normal, or none. So the formula to calculate the total I/O bandwidth is read bandwidth plus 3 times of write bandwidth in case of a high redundancy, and 2 times of write bandwidth for normal, and 1 factor as if you don't have redundancy. And in terms of total IOPS required, it is going to be read IOPS plus 3 times of write IOPS if high, 2 times of write IOPS if normal, and 1 times of write IOPS if none. So it provides network throughput estimation for size as well as IOPS consideration when selecting between different data management options such as a virtual machine database or bare metal or Exadata database solutions. Now take a look at a few other analysis from the AWR reports. Since we are going to do a sizing or looking at consolidation, we have to also look at what it shows for average synchronous single block read latency values. So think of if the average value is greater than 40 millisecond, it means, or it translates to, latency is too high there. Average active sessions, core count of source database. So if average active session is greater than the total number of core count present on the physical or virtual system, that indicates it might be a CPU bound thing. IOPS workload in MB per second or workload in IOPS for the source database. And to calculate the ratio of IO bandwidth to IOPS can be used to characterize the source database workload as either OLTP or decision support system. Another factor you can think about, if number of OLTP hours is between 40% and 60%, the source database can be classified as mixed. Otherwise, if it is less than 40%, then it is decision support system. If a workload type you have identified as OLTP and IOPS is greater than 5000, then it could potentially benefit from consolidating to an Oracle Exadata-based cloud service because of it has flash cache, and workload can get benefit from the flash cache. Workload is likely to benefit from Exadata storage-based solution offered by Oracle Cloud Infrastructure, especially if your workload is a mixed workload because of technologies such as database in memory or Exafusion and storage processing, which are available on Exa kind of systems. So in case of a cluster database configuration types of source DB, so it could be either policy managed or admin managed or non-clustered. So the suitable platform could be either virtual machine database because they provide real application clusters, or anything related to Exa. So Exadata Cloud Service or Exadata Cloud at Customer, autonomous databases or ATP, they all support real application cluster. One of the goal for you to look at if the buffer cache hit ratio of the source database is more than 98% for OLTP workload, and if that is not the case, then you might need certain tuning, or you have to factor the buffer cache to eliminate excessive IO load prior to capacity planning. So workload type estimated OLTP and average wait time for event log file sync wait at the source database. If it is more than 10 milliseconds, that indicates excessive time to write redo information to redo log files or disk, and possibility to slow disk, or maybe because of unbatched commits. So that might require tuning the sequels in terms of commit frequency, use of no logging options, or checking disk contents, and also factoring the enhanced disk throughput. So that should be also factored within the capacity planning for any new infrastructure. Another interpretation could be if workload type is estimated as OLTP and average wait time for event DB file sequential read is greater than 15 milliseconds, that indicate poorly tuned SQL or slow IO subsystem. So investigation of SQL statement performing many disk reads and IO subsystem for poor read times is definitely recommended. If a workload type estimated is OLTP or DSS or mixed, and IO workload in MB per second is greater than 500 MB per second, so average synchronous single block read latency value of source database is greater than 40 milliseconds. So in that scenario, again, Oracle ExaCS or Exa Cloud at Customer or ATP dedicated is recommended for the destination, because that way you can prevent the high IO rates which might impact the OLTP performance. So in next module, we will look at how to interpret sizing requirements. Till now we have covered some of the observation or data points from the AWR reports, and Next, we are going to discuss how to interpret the sizing requirements, and the tool we are going to look at is AWR Miner. So AWR Miner takes data from AWR performance views, and it is able to provide a graphical insight, and we will be interpreting using an example. So now I will see you in the next lesson.